Okay, we're going to talk about chapter 10 now. And what page was that on here? Let's start with the screen share. Kind of exciting. We get to do some new stuff. We are on, sorry about that. Page 55. Page 55, rotation. All right. So we're going to start with some kind of useful nuggets and some definitions here. So this is going to be, what do I want to say here? How about I say it this way? Chapter 10, we are going to redo chapters 1 through 8 using rotational ideas. So it's a review in one sense, and yet it's a lot more complicated in another. So, and it's all in one chapter. This gets really exciting. And if you're a mechanical engineer, you are going to love this chapter. If you've had as much caffeine as I have, you're going to love it. So theta, this is a lot like the variable we used to have, x. Theta is going to be angular position. Delta theta will be angular displacement. Omega, that's angular velocity. Notice the units here. Because we're going to do calculus on these problems, we need to use radians. Degrees doesn't make sense if you do calculus. So there's a note below. We'll get there in a second. Alpha, we've already discussed this. That's angular acceleration. That's radians per second squared. I'm going to write the period like this. So that's a period. That's the time for something to go around once. And F is frequency in hertz. Okay. So hertz, you could think of the German word for heartbeat, H-E-R-Z, or is heart. So Hertz. And then hertz kind of looks like that. 1 per second, heartbeats 1 time per second. Maybe this helps you remember. Now, regarding these units, okay, 1 revolution is 2 pi radians is the same as 360 degrees. So we need to know all of these. For example, a lot of times people like to think in RPMs. If you're dealing with something that spins at a certain number of RPMs, that's equivalent to a certain number of radians per second. So in physics, we deal with radians per second. When talking with the rest of humanity, they usually like to understand RPMs or hertz. Okay, this is right because it makes sense for doing calculus, and this makes sense for communications because it's a standard unit. All right, so look at this. You probably recognize these equations. Take a second to look at those. Maybe I can even make it slightly bigger. In this case, I hope you realize they're just the same as the kinematics equations we used before. Delta x is VT plus 1/2 AT squared. Only now delta theta is angular displacement. So if I could, let's just underline the angulars in all of these. So we're doing the same thing as before, but we're adding the word angular everywhere. As a result, we get angular displacement, angular velocity times time, angular acceleration, 1/2 times time squared. This is the V final squared equation. If you look at it, it's the same equation. V final squared equals V initial squared plus 2 alpha delta theta. Okay. And this is the other of the big three. Okay. So now, strictly speaking, theta is not a vector. It's not a true vector. It acts like a vector as long as, this is a big word here, or a big point to make, as long as the axis of rotation remains fixed. So essentially, if you're talking about a disk that spins about an axis like this, it's totally reasonable to treat theta as a vector. But if it's a spinning top where the axis of rotation is precessing like this, then it's not. So let's say you had a top that's spinning here on a right, and the axis is precessing about, this would not be a true vector in that case. However, for a lot of problems, let's say you've got a flywheel in an engine, it's spinning on an axis, or a tire of a bicycle that spins on an axis, or a human being that's a figure skater spinning on an axis. a lot of typical problems, we can get away with this. Any questions about that before we scroll down? This is page 55, rotation definitions. Okay. So this gets tricky. The vectored nature of these is not obvious. And so this you'd better listen to. Let's say an object is going this way. All right. So you would probably call that what? Counterclockwise, CCW. A physicist would call that K-hat. Now, how do these relate? Let me see if I could show you on the whiteboard. And you've got this here. So this is something that at first pisses people off. You're like, what are you talking about? It's not rotating about K-hat. I argue it is if you get used to this one fact. Okay, so this is a big deal. And when you're coding it, we need this. So this is the K-hat direction. If I call this I-hat and this J-hat. Remember in chapter 3, I made us test right-handed coordinate systems? Everybody get out your right hand, get comfortable, line up your right hand with I, curl it to J, your thumb comes out of the page, K-hat. That's why I drew a dot. Remember, dot means out of the page. X means into the page. I remember this by the dot is like the point of an arrow coming out to shoot you. And then the X is the feathers flying away. So again, into the page is an X. So I goes to J, goes to K. If you're not using your hand right now, you should, because we're going to do this a lot in the next few chapters, as in every day, multiple times a day. It's better that you get used to doing it. I goes to J, goes to K. So now think about something that is rotating this way. Let me get a different color. Imagine you had something that's rotating in this circle this way. So if it's moving this way, take your right hand, curl your fingers in the direction it's moving. It's curling around this way. Now, sorry, lefties, this is a right-handed rule. So you got to use your right hand. Okay, so it's going this way. Notice which way my thumb points. If I line up my fingers correctly and I curl them around, which way is my thumb pointing? K-hat. We say the axis of rotation points K-hat. If you're going counterclockwise, the axis points K-hat. If you were going clockwise, it would be the other way. My thumb points into the page. So when we're talking about rotational vectors, we are talking about the direction the axis points. We are not talking about the direction the thing moves. We're talking about the direction the axis points if you use your right hand. Questions on that?
So that would make counterclockwise positive all the time?
Well, it depends on how you draw your coordinate system. But generally speaking, yes. This is one standard math. This is actually the Python convention too, right? I goes this way, J goes this way, and K is out of the page. You remember that from your vectors. So in this case, we're also saying, now the other standard one that you see in math books all the time is that this way is X, this way is Y, and this way is Z, right? Maybe you've seen that before, as in fact, I know you saw it. We did it last time when we did that triangular center mass. This is the other kind of standard one. Sorry, that's a little... where sometimes they say X is out of the page, Y is to the right, and Z is up. But in that case, then Z hat would be upwards, and the rotation would be in this plane here. Does that address your question, Esteban? Or did I get off topic?
No, yeah, you got it. So if it was lying, the circle is lying on the XY plane, and it's still the same thing, right? It's turning counterclockwise, and it's positive because it's going in the Z direction.
Yeah.
If it was spinning the other way, it would be going negative Z.
Yeah. And if you think about what we did in Python, you remember how we could rotate the vector pictures and spin it around, right? The XYZ orientation, as you spin the picture, right? What you're really doing is moving which way the camera is looking. But the orientation of X, Y, and Z relative to each other is always such that I goes to J, goes to K. In this case, I got to switch hands here. Notice in this case, I goes to J, goes to K still works. And that's why I'm always going to say, check that you drew this correctly before you trust it. Because if you screw up one of the axes, you'll get minus signs and miss points for a minus sign, and you'll be pissed. So always check your coordinates. I goes to J goes to K. All right. All right. Other questions? If you do, blur them out. I'm going to go back to the screen share. All right. So here's the rule that I just did. Line up the fingers with the curl your fingers in the direction that it's moving. Stick out your thumb, and your thumb lines up with the disk's axis. And then watch out. You know, physicists, they can't do math. They have to just flip the coordinates. Sometimes I will actually call clockwise positive. Think about it. If everything in a problem is going clockwise, physicists would be like, dude, I don't need these minus signs in my life. I'm going to flip it and just call the negative direction the positive direction. And so that would basically be like inverting your Z hat, right? Or something like that. So whatever. All right. Sometimes physicists will be annoying and do that. If everything's going clockwise, we call clockwise positive. All right. Now, let's look at this. These equations, look carefully, they look almost identical to the ones that were up higher. Let me see if I can get them both on the page at the same time if I do this. Oh. There we go. I can just barely get them. All right. So I want you to look at these equations up here and these equations down here. And notice they're the kinematics equations. And it turns out if you multiply the rotational kinematics equations by R, we can actually get back translation, except instead of X, we use S for arc length. Arc length is S. And that's the distance traveled along a circular path. V tangential, if you recall V tangential from chapter 6, that's the tangential speed. Be careful, that's not the same thing as angular speed. And so it becomes very crucial we read problems carefully. Are they asking you for speed, or are they asking you for angular speed? What about acceleration? Are they talking about centripetal acceleration, tangential acceleration, total acceleration, or angular acceleration? They are all related, but each one has a different physical purpose, meaning in calculations. So notice we know that V equals R omega already. We know that A tangential is R alpha. We know this from chapter 6 already, the centripetal acceleration. So, and maybe we didn't know this one already, but that might be a new one. So the idea here is these are equations that relate the translational quantities, S, V, and A, tan, to the rotational quantities, theta or delta theta, omega, and alpha. The total acceleration, so if somebody just says acceleration and makes no other claim or no other modifiers, that usually means total acceleration. And that we talked about last time. You could get this direction here and you get these weird equations. And again, why do we have to use radians for physics? If you want the units to work out for these last equations like R omega squared, it only makes sense if you use omega in radians per second, not revolutions per minute. So that's another reason we have to deal with radians. Any questions about these things right now? Okay, let's do a problem because you don't really understand anything until you start doing problems, right? Whoops. All right, let's start simple, 10.1, okay? So take a second to look at it. All right. I'm getting a, whoops. Got this wrong marker. Let's see if I get another one here. Ah, there we go. Okay. I'm just writing down the rest of the question. So part A. What are we supposed to be finding in part A? Let's talk about this as a group while it's up on screen. What symbol am I supposed to be solving for?
Alpha.
Alpha, fish swimming left. What is this? It says initially rotating at 33 1/3 RPMs. What parameter did I give you there? Somebody other than Esteban, give it a shot.
Would it be angular velocity?
That's right. And it says initial, so it would be
Your
omega initial. Now, remember, don't write W. This is not W. Don't say W. Say omega initial. And that should look kind of like a curly W, not a pointy W. It's not a W. It's an omega. We tell the difference by drawing it curly. All right. This one, I got that. That's just radius, R. And this one, T. Okay. All right. How about this one? What are we supposed to get here? What symbol is total acceleration?
So that's AC and A10.
Yeah, or it's just A, which is equal to, like you said, we have to combine AC squared plus A tan squared, right? Okay. And then total distance traveled by a point on the rim. What parameter is that?
Arc length. S.
Yes, arc length. So this is going to help. This is going to help us learn these terms. I'm having trouble speaking today. That's the, okay, whatever. Let's do it. So part A is get alpha. Part B is get A, or A total, if we want to clarify. And part C is get S. That's our goals. All right. Tell me what to do. You know what to do. Tell me what to do. What's one thing you might try? You don't have to tell me the full answer. Just tell me the next step. We identified what we're looking for.
Could you create a table like the kinematic equations?
Exactly. Don't overthink it. So now we want to do you want to do rotational or translational kinematics? What do you think?
Rotational.
Yeah, because it's chapter 10 and it's our first problem. So then what are the parameters we had? Well, I'll just remind you, we had X, V initial, V final, A, and T, or sometimes we called it delta X, right? So what would be the equivalent that we would write now in rotation land? And then was that Luke?
Yeah.
Yeah, keep rolling, Luke. So what do you think we would write instead of these?
So change in X would be angular displacement.
Change in theta. What instead of V initial we get?
I want to call it W omega.
Omega initial. Good.
And then omega final.
Uh-huh.
And then what was it called? I don't remember what it's called.
Fish swimming left.
Yeah, fish swimming left.
Alpha.
Alpha.
And then time. Got it. So we're going to do a table. All right. So that's a good idea. Nice job. All right. And so help me out. What do we know for part A? You want to keep rolling, Luke?
Sure.
Give me one thing you know.
We have omega initial, but it's in RPMs. So do we
Okay.
convert that to radians?
Yep. Not to radians, but
Radians
to
per second.
Yes. So I'm going to write this out. We know RPM means revolution per minute. So then I want to get this to radians per second. Let's get rid of the revolutions. What do I need to do to get rid of those revolutions here? Multiply by what over what?
1 revolution over 2 pi radians.
Do you think that is going to work?
Oh, no. 2 pi
So,
radians over 1 revolution.
Absolutely. Flip it. Good job. And so this is what I do too. I'm just like, oh, whoops, that's not going to work. Trial and error, right? This is a valid way to do it. Okay, then I need to get rid of this. We're going to run out of some room here. All right, then what?
And then 1 minute over 60 seconds.
Now humor me. Pi is about 3, right?
Yeah.
2 times 3 is about 6, right?
Yeah.
6 over 60 is about 1/10. So estimate the final answer. Estimate it.
Like 3.3.
3 and change. Now, this is a good thing to do because what happens is people sometimes forget to multiply or pi. And in particular, when you're doing it the other way, people do times 60 divide by 2 pi and forget the parentheses and forget to check. Basically, do this. Every time you convert, it should change by a factor of 10. It should either get 10 bigger or 10 smaller, depending on which way you're going. Now, at here, you can plug all these numbers in and we got it. And then let's see what it was. Does anybody have the number offhand? Go ahead and punch it in for him. I'll do it as well. Everybody just check. So 33.3333 times 2 times pi div 60. I got 3.49. So that's about what he was expecting. 3.491, let's say. Radians per second. Sorry if that's sloppy. That says radians per second. Okay. Sorry about that. Okay, cool. What's omega final? Somebody else. I'll give him a break now.
0.
What's the key word?
Comes to rest.
Boom. 0. Nice. What else?
You have time.
Yep.
10 seconds.
We know 3 out of the 5 things. I bet we could find the other 2 with some equations. Agreed? I don't know how many angles it rotates through, and I don't know alpha. Aha, that's what I'm looking for. Okay, so how would you approach this one? What equation would you do? Would you write the, I know this is going to sound crazy. I'm going to say it in X. Would you write the delta X equation, meaning the delta theta? Would you write the V squared equation, meaning the omega squared equation? Or would you write the V equation, the omega equation? Which one?
Oh, I do V square.
V squared would work, except that's got delta theta in it and delta. And
Oh,
alpha.
yeah, you're right. You're right.
So you're right. So it turns out that's a good guess. So give me another guess.
Would it be the omega final equals omega initial plus angular
I
acceleration?
think that's going to
G?
do it. I think. Let's double check. So what you would do is, generally speaking, write down all 3 and check, right? Well, let's check. In this case, we've got omega final. We've got omega initial. I've got time. So in this case, I've got it. So what is alpha? Oh, wait. What's the next thing that you do before we do any algebra?
Cancel out any zeros.
Plug in the zeros. Okay, so now that makes it a little bit easier, right? So what do we get? I think it's negative omega initial over time equals alpha. We've got omega initial, we've got t. What should we always do with this algebraic equation?
Check units.
Yeah, you guys are doing well today. Yeah, I love it. It's kind of like Mr. Miyagi making that guy paint the fence over and over by suffering. Now this stuff is like, you got it, and you could just learn new stuff quickly. So I'm excited for you guys. The cool part is now you're there. Oh, so stoked for you guys. Radians per second divided by second. So I know I'm a mean curmudgeon all semester long, but it's for these moments that you do this. You have punished yourself, so this is so automatic. You can actually learn this chapter quickly now. Radians per second squared, that's a unit of alpha. Got it. All right, I hope you're having fun. Let's go back. I think you could plug in numbers and you'll be good. So let's go and see here. I think that was part 1. We've got it. Notice angular acceleration is negative. Does that make sense? What do you think?
Yeah, because it's slowing down.
Yeah, so we're assuming that this was positive and we slow down, so that makes this have to be negative. All right, so now total acceleration. Any ideas how we get that? How about we read the equation sheet? It's this. Well, wait a minute. Look at this. This is a fancy way of deriving this. Let's kind of work this out really quick, okay? So here we go. We could figure that out. So now, in theory, we know this. And then it says, I want to point something out. Ding, 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 alarm bells going off. Can we use this same list of knowns for part B?
No,
No, why not?
you have a different time.
Different times. So we're going to have to make a new delta theta, omega final, omega initial, alpha, and t. Now, some things are the same. Omega initial is the same. Alpha, that we just figured out, is the same, but the time is now different. And so we're going to have slightly different things here. Sorry, that's a little off the page there. So we've got this, and this, and now it's figuring out these things. Now, in this case, we are told A total is equal to the square root of the centripetal component squared plus the tangential component squared. If you think about it, here's a point on the edge of the record. It's going around and around and around, right? It's got some speed here. Whoops, let's say it's going this way. It's got some speed. And so as a result, there's also some omega associated with that. But there's also, working against that omega, is this alpha term. There's an angular acceleration. And so the particular point out here is feeling forces this way and that way. Or I guess in this case, there's a force this direction, right? So this particular point has a force against its motion, slowing it down, and towards the center, keeping it in the circle. All right. And so that's actually the molecules of the record holding itself together have to exert these forces on this outer molecule. If those molecular forces aren't strong enough, if you spin it fast enough, it will explode. Believe it or not, they're having this issue with Formula One race cars, I read the other day. I'm not a big race car fan, but one of the things they're doing is they're putting flywheels inside of Formula One cars. Maybe they've already done this. And they had this problem where the flywheels were spinning so fast they could explode on them. And man, that's dangerous. But you can actually save some of the energy as you brake into this flywheel, spin it up, and then give it back when you come out of a turn. And I guess this is a good thing. Anyways, there's applications of this. That's what I was alluding to. Point being, that's where this equation comes from, all that picture. Whatever. Can go over it more if you didn't understand that later. So A total is equal to, when we're in rotation land, usually I would say this is r omega squared, and then we've got to square it, plus tangential acceleration. It's not your alpha, it's r alpha. And so we see if you could figure out omega final at 2 seconds, we could plug that in. I know the radius because that was given somewhere in the problem. If I know alpha, well, we've already figured that out in part A, I could get the total acceleration vector. What do you think?
That's just chapter 2.
It's just chapter 2. So we beat the crap out of chapter 2 in the hopes that this would be easy. I hope it's kind of making some sense. Let's go into here. So just kind of looking through it, notice here the R factored out. I got some numbers. That's great. Okay, so you can plug in numbers. All right, whoops, where is it? Let's go back to here. Determine the total distance traveled by a point on the rim. Okay, we want this point on the rim. So again, we're looking for S. Going back to this, we want the total distance traveled as it comes to rest. Should we use this table or this table? Which one applies? The lower or the upper?
The upper one.
Upper one. That's for it coming to rest. We use that right there. So now, what do I need to do? I want the angular distance traveled. We said that's the arc length, but I know that arc length is equal to S times delta theta. Well, I bet there's a kinematics equation I could use, and it's probably delta theta equals, somebody tell me what delta theta equals. Try it without looking at the sheet. See if you could tell me what it is. Remember, it's just like the delta x equation, which was Vt plus 1/2 alpha t squared. What is the equivalent to this? If we want delta theta, what's the equivalent?
So it'll be omega initial t plus 1/2 alpha t squared.
Exactly. And so, aha, we know this, now we know this, we've got that, we've got it. So we could get delta theta. Once we get delta theta, we know R, we've got S. Sweet. What do you think? Not too bad, right? The main thing that's different from chapter 2 is we've got this extra mess down here to deal with. It's just a bunch of equations, but if you can get a feeling for not only doing the math, but also the physical meaning of these, then you really have this locked. So going back to here, we've done it. That's that problem in its entirety. Let's see what the solution was, just in case there's something that pops out at me. So here's that equation. Then just plug it in, and then great. It looks like I kept track of sig figs. Oh yeah, the radius, I only had 2 sig figs, right? Whatever. Oh, check this out. Look what I remembered to do up here. The radius was 24 centimeters. Don't forget to change that to meters, right? Always the unit. So, okay. Let's take a look at another one. Let's go back to here. So, here we go. Does anybody know where Gaussian is? That's how you say that. Anybody know where Gaussian is? Taiwan. Second largest city in Taiwan. So on my sabbatical, I lived in Taiwan because my baby mama's from there. We took the kids over there, and I did physics problems in a little apartment building all day. And so I wrote this up. And right near where I lived was a train, and the public transit there went in this direction. This is a very crude approximation, but I was riding on the train one day. I'm like, oh, this would make a perfect problem for my class. So I was riding from Central Station to Sanduo Station, and then it starts out with this, it wasn't perfectly quarter arc, but approximately quarter arc. Okay. Now, I Googled this number. It turns out any acceleration larger than that, passengers evidently start to complain. So this is a typical maximum acceleration you want to use for a subway train. Otherwise, your people start barfing, okay, or complain anyways. So it's going to speed up until it reaches this fast. How many miles per hour is that? Estimate. Got it? About? That's about 50 or 60. Okay, so remember to go from meters per second to miles per hour. It's about 2, a factor of 2. All right, 2.2 or so. All right, great. So it's a 200-meter radius. So think about that. 100 meters is like a football field. So this is a pretty big turn. Okay, we're taking a huge turn, small. Okay, now what are these parameters I gave you? It says the train speeds up at this rate. What is that? Is it alpha? Is it omega? Is it S? Is it theta?
Alpha.
It's not alpha. Alpha has units of radians per second squared. So it's
just acceleration.
It's
which
A10.
one?
A10.
It's A10. It's not a total. Remember that A10 talks about the change in your rate of speed. So if you were sitting right here and you're moving and you speed up, that's a component of acceleration tangent to that. So if you're moving tangent to the circle and you speed up, that's talking about A10. Okay, good. So we know A10. And this, what is this? Is that theta, omega, alpha? A, T. What is it?
That's V.
That's right. And sometimes, because it's moving in a circle, we could call this V. Some books call it V tangential, V tangent to the circle. Either one would be an acceptable answer to me. All right. All right. So now determine, what are we supposed to figure out here? What are we trying to find? What symbol is that?
Theta.
Yeah, or delta theta, depending. So typically, if we say that you start at theta initial, if we always set that to 0, not always true, but if we set that to 0, delta theta and theta could be used interchangeably. So you're either going to write delta theta or theta, either one. All right, good. And then here, determine times. Okay, got it. Sketch plots. All right, so what should I do to solve part A? Let's just work on part A. What would you do? Don't have to tell me the answer. Just tell me how you would start to attack it. Take a second to think while I erase. You can do whatever you want. Sketch some notes out. Give me a second to get caught up. Okay, what do we do? Any ideas?
I guess you could start with the table again.
Sure thing. Okay, so are you wanting to do rotational kinematics or translational? What do you want to do?
Rotational.
Okay, so you could write down delta theta, omega initial, omega final, alpha, and T. You could do that. Now, do you agree we could multiply all these by r and get S, V initial, V final, A tangential, and time? That's a weird step, but you could also do it that way. Do you agree?
I didn't know that, but now I do.
Now you do. And I want to point out, which way do you think is wise for this problem?
To find the angle, I mean, I would say to use rotational first, right?
I would actually use this because I already know this is 0. I already know this is 25.7. I already know this is 1.4. And I'm
And
leaving
then just
off
go the other
units.
way around.
Yeah,
I
and
see.
so you could find this, then
And then go
divide by
backwards.
r and get theta.
Got it.
Now, what you would have to do is divide this by r and then divide this by r and solve for theta. And so you would have to divide two numbers by r. I would only have to do one. It's the same, right? Same procedure. Cool? And that's why I wanted to show you this. So at this point, you could plug in numbers and get it. Let's go to the next part. Well, actually, let's look at that answer. So there's a mega table if you're wanting to see everything. Ooh, milliradians. Ooh, that's kind of fun. Okay, so the angular acceleration is tiny. Look at how small that is. All right, that's cool. Again, if you have a large radius like that, you end up with a small angular acceleration, a small angular speed. Okay, that's cool. So now here's what I did. I just went this way. I took everything and then I don't know. I guess here's the angle. Okay, so and then again, notice you output the angle in radians. That's cool. Great. So if you have 90 degrees to cover total, right? You've got the remaining whatever, what is that? 22.4 degrees, which converts to this many radians to go. All right. So that's that question. Great. You can check it that later. Okay. Finding the elapsed times. We're going to use another kinematics equation. I'm going to jump to the solution just so you can take a look at it. I just did, you could use translational kinematics with the tangential acceleration and get the times for the first one. And then for the second stage, I used angular kinematics. So we see this is a little different than chapter 2 because there's a few tricks where you could multiply and divide by the radius and get different equations that are easier or harder to use. So, okay. Yeah, isn't this weird? First stage, arc length kinematics. Second stage, angular kinematics. Okay, so whatever. I did some stuff. Check the sig figs. Ooh, let's go back and see the question here. Okay. So this one is an interesting thing here. Sketch plots of A tan versus T. What do you think that would look like, people? So we're going to, okay, so A tan, AC, and A total. Try not to look at the answer right away. If you can understand something graphically, usually you understand it more deeply because you not only understand one instant in time, but all instants in time. So we want to plot A tan versus T, AC versus T, and A total versus T so that we can really lock in this understanding. So tell me, forgetting the units for right now, what do you think A tan versus time looks like?
Is it a straight line up until a point, then it goes to 0?
Something like that. And I don't know the exact lengths of time, so let's just say it looks something like that. Excellent. All right. What about AC versus time? First, give me an equation for AC. This is the trick when you get these, sketch the plot. Give me an equation for AC. What is any equation you know? I'll tell you if it's a good one or a bad one. Take a guess.
V square over R.
That's a good one. However, it's easier if we use R omega squared. But you could use V squared over R if you want. R is a constant, right? So what is happening to the speed? Is the speed changing linearly? Is the speed changing quadratically? Do you know any equations for the speed as a function of time? Right? The initial is 0. It's A tangential, which is a constant, times t squared, right? So what is this plot going to look like?
It's a parabola, right?
It's a
When you
parabola.
called, I was still at work.
And then, whoops. What's going to happen to it right here?
Be constant.
It's going to be constant, not 0, because omega is constant. Absolutely. Got it? Cool. So that's looking good. So then what would A total look like? These numbers squared plus these numbers squared, square root. Where do you think you get the largest amount of total acceleration?
What do you mean?
Okay, remember, okay, so A total is equal to the square root of AC squared plus A tan squared, right? That's our equation that we can use. At what point in time will we have the largest A total?
So it would be when AC and A tan equal?
AC and A tan may never equal,
Last time I got there,
but it's when
was
both of
like
them are
another
large.
Can you read this?
I think
Okay.
that's what you meant. So let me put it this way. This number right here and this number right here are effectively the same. However, this number right here and this number right here are very different. So the point in time just before the tangential kicks off will be the largest total. So when we look at it, let's go see what these look like. By the way, one of your quizzes in the rest of the semester has something like this where you're supposed to guess what plots should look like. So if you think I'm wasting your time, I'm not. Let's go look at those. Look at this. This is what it ended up working out with these particular numbers. I don't know if you could see that very well. I should have made those grid lines more faint. But we could see here as time goes on at about 18 seconds, the tangential cuts off. And then just before it cuts off, the total acceleration is slightly larger. And once tangential goes away, you don't really see it. But remember, right here, AC and A total are equal at this point if A tan is equal to 0 at that point. So that's the 3 graphs. All right. What do you think? Ooh. It says determine the maximum force the train exerts on a 70-kilogram rider during the turn. How do you get force?
Force equals MA.
Which A?
Because they're
Would it be A10?
It's not A tan.
I think it might be AC.
It's not AC.
Oh, wow.
It's A total. That's what A total means. So keep in mind, in previous problems, we always had F equals MAC, right? That was for uniform circular motion. In chapter 6, we did everything we could to set a, whoops, not a, gee, what am I doing squared there? Sorry about that. Hold on, that makes me want to puke. There we go. We often said force is equal to MAC because A10 was equal to 0 in all those chapter 6 problems, right? So really, force depends on the total acceleration. So this tells us what all these accelerations mean. Alpha, well, let me just do this in just a second. Let me write this up before I, okay. That is what total acceleration is. All right. So maybe we could go to the board here and, all right. Well, okay. Before we do that, I'll summarize in just a minute. So you have to use total for the force. Everybody cool with that? That's just a fact. Next, contemplate a ball hanging from the ceiling of the train. How is the ball going to move around as the train moves along the track? Okay. You've got this, say you're sitting on the train and you have this, well, it's not a ball, it's a weird little flashlight, I think. Ooh, that's kind of cool. Never done that before. I was thinking about what it would look like if I just held up a mirror to the Zoom meeting. I haven't done that experiment yet either. But let's say you got this hanging here. Let's erase all this. So you're sitting in the train. What's it going to do? Is it going to hang straight down or is it going to hang at an angle as you move?
It's going to be at an angle.
Yeah, as you accelerate forwards, it's going to hang like this. Well, okay, so let me sit like this. As you accelerate forwards, we'd expect it to hang like this, right? So the tension is going to have to be pulling this thing forward if this is going to accelerate. So this causes that if you accelerate forwards, it causes a fictional force backwards. So that's what we expect right there for that. However, as you get going faster and faster, you need acceleration towards the center of the circle. So it's going to hang not only backwards, but also out at an angle. And then at some point, you're not accelerating forwards anymore. It's just going to hang out at an angle towards you, right? Or towards the outside of the turn. So if you could imagine, that's what those graphs look like physically. They're describing, in a sense, the angle at which the ball will hang as a function of time. The tangential talks about the front-back angle. The centripetal talks about the towards the center, away from the center angle. And so that's what would describe the motion of this thing. And the net angle relates to the total force or the total acceleration. I don't know if that made any sense, but that's what I'm trying to get at with that. So far, so good?
Wouldn't it lean towards the outside of the circle?
Exactly. And again,
Okay.
Did I say that? Yeah, sorry. I meant
it sounded like you were.
Yeah, so if I'm assuming I'm turning this way.
Okay.
So I'm going that way.
Gotcha.
So that means you're right. It will hang back and out away from the center so that the string pulls it towards the center. The string exerts a force towards the center, but in order to do that, this has to be towards the outside, right?
Yep.
It tends to remain at rest. And so as a result, the train is going to move and pull the top of the string ahead, which then pulls this mass with it. And then again, the train will curve away, and then this will pull that with it. So basically, this thing is hanging still, and the top of the string is moving in different directions, and then it pulls this along with it a second later, or a nanosecond later. All right. Okay, so what do we learn about all this stuff? Right? So we've got alpha is the angular accel. A tan is d dt, meaning change in of speed, tangent to circle. So, right, this one is talking about your change in speed. And then AC is required to cause the force towards the center. That's r omega squared, or v squared over r. And then it relates to force keeping in circle motion, right? And then A total, this marker drives me crazy. Let's go to a fistful of black markers somewhere here. A total, that's AC squared plus A tan squared, square root, relates to net force. So now that A tan is non-zero, this tells us how we can analyze problems where they're not only going in circular motion, but they're going in circular motion and changing speed. We saw that you could use kinematics either way. You could use it with A tan and V tan and do regular old translational kinematics, or you could do rotational kinematics. All right, let's get back in there. Or any questions while I've got this all up? That's kind of the big picture here for rotational kinematics. This is the new stuff. Everything else is chapter 2. Keeping these straight is crucial. By the way, we have a lab later where we do coding rotational kinematics, and all that I hat, J hat, K hat stuff matters. All of this stuff matters. And yeah, and it's sneaky. All right, so here's one where I gave you the graph and ask you to interpret it just like chapter 2. Here's one where I give you something here. What do you notice about this one? What's special about 10.4?
It's not constant acceleration.
Exactly. So what do you have to do?
The hard work.
Calculus. It's pretty easy. But yeah, okay. So it's the same crap. And now what about this one?
More calc.
Yep. Separation of variables. Chapter 2. By the way, here's a weird one. I used to live next to Nanza Export Processing Zone Station. That's a real station. And the next stop was actually, look at this weird title, Oil Refinery Elementary School Station. Very weird. The train looked almost exactly like that. And so here's a case where you could have straight line motion, then angular motion, and then straight line motion again. So here you have to flip back and forth, do angular, translational, blah, blah, blah. Gao Shun in the house. All right, whatever. Here's one, a plot. I gave you an alpha versus T plot. So all the same stuff you learned in the plotting of chapter 2 applies here. Oh man, here's 10.6 and 3/4. What is this one? Oh, look at the units. I give you an RPMs, centimeters, milliseconds. So, oh my gosh. Okay, so this is, yeah, if you could do those 6, I think you've got them down. Maybe we'll end with this, or well, let's see. Okay. So let's you could do those problems later. Great. Relating rotation to translation. We've seen like this thing and this and all this crap, and maybe you remember this as well, the period. Oh, whoops, I forgot a parenthesis. Oh, well, good thing it's not a code. Take a look at this. Position, the new angular quantity is theta. Velocity, omega, etc. Now look at this, mass. Mass is now going to become a new quantity called moment of inertia. Rotational mass and regular mass are not the same. Force is going to change to torque. Momentum is going to change to a thing called angular momentum. So let's try this out. 10.7 on page 58. You've got the table there. Try to use that table. Let's take a second to do this and see if you can write the translational equivalents, or excuse me, I want you to write the rotational equivalents. Basically, fill in this side by looking at these and using the symbols up above. Take a minute to do that, even though it seems stupid, right? It's getting used to these symbols. Let's do one together. I want to rewrite force equals ma. What is the equivalent rotational statement? Sum of what?
So force is a torque, right?
Sum of torques, it's a vector, equals,
Oh, omega.
nope, not omega. What's the rotational equivalent of mass?
Oh, inertia.
Yeah, moment of inertia. So don't say inertia, say moment of inertia.
Okay.
Inertia is mass. Moment of inertia is rotational mass. It's a subtle thing. So moment of inertia.
An alpha.
Alpha, yeah. And notice which things are vectors remains constant. So let's try another one. Sum of torques should equal instead of momentum, we are going to use
Angular momentum.
angular momentum. Now let's take this a step further, people. This equation, if there's no net force, what was conserved?
Momentum.
Yes. So if there's no net torque, what is conserved?
Angular momentum.
Yeah. We just learned a new conservation law by looking at these symbols. Isn't that cool? So if there's no net force, we know momentum is conserved. We don't know what angular momentum is yet, but we know if there's no net torque, angular momentum is conserved. That's chapter 11. That's the one piece of this we do in the next chapter. It's nasty. All right. What about kinetic energy? Let's skip down to here. Rotational kinetic energy would be 1/2 I. What's the equivalent of V?
Omega.
So we could see how you can get all. What about power? Torque times omega, right? It's cool. So we actually know everything already if you're good at this table. So you could write the rest of them at home, and I did put the answers in the solution for you. So, all right, that's cool. Now, this is to foreshadow. All right, so we are not going to have time to pick this up now, but maybe we'll try one problem and show you. I just want to point out this one sentence. Moment of inertia is a world of hurt. Okay? I can't say it any shorter than that. Mass is pretty freaking simple. It's just put the thing on a balance. What does the number say? Now, let's focus on what mass means. Mass can be described best as your resistance to changes in motion. The more mass you have, the more you resist change to your motion. You don't necessarily resist motion. For example, the planet Earth is moving around the sun right now. If you take a little mosquito and stick it out in space, right, it's not going to change motion very easily because its mass is so huge. And you would get rid of one mosquito that's one less to bite us. So that's a net gain. So please do that experiment. Now, okay, great. Yeah, you're going to hear me say this term rotational mass in lieu of the full term moment of inertia. I just want to be clear that there's a difference between mass and moment of inertia. So sometimes I say rotational mass. I don't know if anybody else in the real world says that, to be honest. But look at this. I just want to point out it. Moment of inertia talks about resisting change in rotational motion. So look at this sentence, underline it, become one with this sentence. Moment of inertia describes the tendency to resist change in rotation. All right. It depends on 4 things. Obviously the mass, but also the shape, the axis location, and how the axis is oriented. I will point out just a couple of these things. Look at this. The moment of inertia, whatever this quantity is 1/12 ml squared when you put a thin rod of length L and put the axis through its center. However, if you put the axis somewhere else, it's a different number. Now look at this one. If you put the axis through the center of a wheel, it's 1/2. If you put it through the center of a disc this way, it's 1/4. Look at this plate. It's 1/12 if you do it this way. It's 1/12 of some other thing if you do it this way. The fact is, this matters. How the object is oriented. It's not enough to just throw something on a balance anymore. You need to know the axis location and orientation. You need to know the mass, and you need to know how it's distributed. Is it a solid sphere? Is it a spherical shell like a basketball? They're not the same. Is it a thin ring? Okay, and there's a few more shapes that are going to be in here later. So, okay, questions about this before we go on. Mass and moment of inertia are very different. Mass, stick it on a scale. Moment of inertia, know all of these 4 things and carefully analyze it. So now we see why there's a whole chapter 10. You might be saying, isn't this just going to be freaking easy? Just this one letter right here takes like a whole day. So we'll focus on this next time. So look at this. Every shape has an infinite number of different possible moments of inertia. If you can't see that this is a lot harder than mass, I don't know. Yeah, that sums it up. There's an infinite number of moments of inertia for every single shape in the universe. So we generally stick to some easy ones. All right. Maybe let's try this. You know what?